Hello, and welcome to Julia Programming with a Data Scientist. My name is Dr. Randy Davila, and today we will be understanding artificial neurons, part 1. If you like my description and you like my videos, please give my video a like down below. And if you really like my videos, please subscribe because I'll be putting out new videos every week. Now, with this lesson, I'm going to start with a story. So I'll go ahead and start reading. Imagine this. Imagine you are a toddler and have no sense of length or of weight, maybe mass. Imagine you don't understand the world around you. For example, you might not know that the size and weight of objects can be related. I don't know. I'm just a mathematician, data scientist asking you to imagine. Suppose next that you are a very simple toddler. Your brain consists of a single lonely neuron, and this neuron decides how you react. You receive stimuli by viewing the lengths of objects in front of you, and bad things happen when you guess the wrong output. In this case, you might view the size of an object and try to guess its weight, and maybe you're penalized if you guess the wrong weight. Even if you make mistakes, I assure you that you can learn, and I want to help you. In this tutorial, I will help you. I will model you with something called a computational unit. In the literature and in popular culture, these are known as artificial neurons and will be a good representation of you. So before we move further, we need to know the basics of artificial neurons. To simplify things, I should tell you that these artificial neurons are actually just mathematical functions. Functions we can use to conceive of an artificial model that roughly approximates the mechanics of a simple biological neuron. Maybe one day, if we understand these simple models enough, we can also explain complex models of the brain. To make the story short, a single artificial neuron receives one or more inputs, which we can interpret as observations or signals, and then computes a weighted sum of these inputs to produce a pre-activation value. This pre-activation value is then passed into an activation function in order to produce a post-activation value, or a guess as to the correct answer, meaning that we observe inputs and then try to predict outputs as a simple computational unit, or a neuron, artificial neuron. In the simplest form, when a neuron observes exactly one input, we have three attributes that are associated with such a neuron. The neuron weight, which is some real number, the neuron bias, which is, again, a real number, and then a scalar activation function, a function that takes the weighted input and spits out an output. So if we look at this diagram here, we see we have an observation that we observe. We have a bias term that are connected with our neuron. The pre-activation value is simply a weighted sum, so weight times our observation plus a bias. And then the post-activation value is this z value passed into a function. And what the neuron spits out is a prediction for that given observation. So again, neuron computation, we observe a single input or signal, x. We calculate a weighted sum on that signal, and then we pass that value into an activation function. And that's what our single neuron model spits out, and is a good representation of you as a simple child. So in order to represent this neuron, or you, we need something called a composite type. And the reason for this is that artificial neurons consist of three fields: a neuron weight, a neuron bias, and a neuron activation function. And from a programming point of view, we would like to represent a neuron in a similar manner. We need three fields. We need a type with three fields. So what we will need are composite types, also called records, structs, or objects. Composite types are collections of named fields, in an instance of which can be treated as a single value. In many languages, composite types are the only kind of user-definable types, such as C, and they are by far the most commonly used user-defined types in Julia. If you're coming from Python, I should warn you that Julia does not support defining custom class objects with attributes and methods. This will be a big leap for you transitioning from Python to Julia, but I assure you it's okay. In Julia, composite types are introduced with or defined with the struct keyword, followed by a block of field names, optionally annotated with types using the double-colon operator. In our case, we might define a neuron as in this case, a static neuron by typing struct static neuron and then give the fields of that neuron. So let's go ahead and do that and say that we want node to equal static neuron. And then, actually, before we assign a variable, we need to define the composite type by typing struct static neuron. I will say W, which will be the weight, will be of type float 64, bias of type float 64, and then backslash phi for our function, and then end. Press Shift Enter, run that Pluto notebook cell, and it's been defined. So now that we have defined our composite type, let's make an instance of this type with weight 3.2, bias 5.0, and give it a linear activation function. Now I see that I have a typo here, which I'll fix and describe to you. So node will be equal to static neuron, pass it 3.2. So this will be assigned to the weight since it's the first in the list of fields. Next will be 5.0, which will be assigned to the bias B since it's the second in the list of fields. And then I'm going to reference myself, the node itself, and say that the function will be x is passed to node dot w, so that accesses the weight, times x plus node dot b. So that's the linear activation function. The weight times your input plus your bias. So I'm going to press Shift Enter. All right, so I see I have a static neuron type. If I want to access the fields of my node or my static neuron, all I have to do is type node dot w. That's my weight. And you might have guessed this by looking at how I defined my activation function. I'm referencing the weight by doing node dot w. And if I want the bias, node dot b, so node dot b, Shift Enter, 5.0. And then if I want to look at my activation function, node dot backslash phi, one second, node dot backslash phi, press tab, I get my Greek letter, and then I can throw in whatever value I want. If I throw in a 0, I should get my bias back because my function is weight times x plus bias. So if x is 0, I should only be left over with my bias. Shift Enter. I see that I get my bias back. If I just do 1, I get that plus that. If I do 2, I get 2 times the weight plus the bias, so forth and so on. So once you instantiate a type, static neuron, you can access the fields of that instantiation by calling dot and then the field. Okay. Now, because we're going to want to change the weights and biases, the weight and bias of our neuron over time, we might need to do something different. And by that, I mean, if I try to change my weight right now, and I say like node dot w, jump down, if I say node.w is now equal to 4, and I try to run that, this immutable struct cannot be changed, right? When we defined our type, our composite type static neuron, we just typed struct, we gave it the fields. We can't change anything once we've instantiated it. So once we've said that node is this, we can't change this field, or this field. But we want to adjust our weights and biases to make our node good at making predictions. We want you to learn. So with that in mind, we're going to make a new composite type called a mutable struct. Okay, and mutable structs, oh, got an error there. Mutable structs allow the fields of an instance of this type to change. So I think the best way is to just show you. So I'll say that mutable struct, I'll call this a neuron. The fields are the W, which is the weight, the bias, which is again the bias, so denoted by B and of type float 64, and the activation function phi. Press end. Okay. Shift enter. That's been defined. So now I'm going to define. I was going to use neuron. I'm going to use node 2 because we have a node above. This will be a different one. So neuron. I'm going to use the rand functionality now to give me a random weight and a random bias. And X will be mapped to node 2 weight times X plus node 2 dot B. So that's the linear activation function. Weight times X plus bias. Press shift enter. Oh, got a misspelling here, neuron. All right, so we can view our weights and biases the same way. Just do node 2 dot W, shift enter, that's my weight. Node 2 dot B, that's my bias. And if I do node 2 dot \5 shift, pass in a value of 0, I should get back my bias. I do. If I pass in a 1, I should get that plus the weight plus the bias. If I pass in a 2, I should get 2 times the weight plus the bias. And now, if I wanted to, I can say node dot W equals 1.66. Oh, not node, node 2. There we go. Node 1, or the original node we made, was a regular struct. Node 2 is mutable, so I can change the weight and I can change the bias. Okay, so now we have a general model to represent this picture. Node 2 currently represents this. It has a weight, a bias, it has a pre-activation value, and a post-activation value, where it just happens to be, in this case, these are the same things. Okay? So then, what do we do with it? Well, let's train our neuron now to be really good at predicting something. And we're going to do this manually. Based off of our higher intelligence, we're going to train this neuron to be okay at something. So now that we have a single neuron model, we next explore how such a model can be used to interact with input data. But first, we need data to work with. The data set that we will use is this Palmer Penguins data set that I've explored a little bit on my channel. This data set consists of several categorical and numerical measurements of penguins and is akin to the famous iris data set. We will load this data set using the palmers.jl package, which will give us access to the following data loading utility. So palmerpenguins.load. Once loaded, we're going to convert this raw data into a data frame using dataframes.jl and assign it to a variable here. So I'm just going to import Palmer penguins and data frames first. Importing Palmer penguins will give me access to the Palmer penguins.load functionality, and data frame will allow me to convert this into a Julia data frame. And I'm going to assign this data frame to the variable penguins. So data frame is going to convert Palmer penguins.load like that. Press Shift Enter. Okay, the packages have loaded. Now the data should be loading. See that it's running over here. Okay, so while this is loading, I'd like to go back up to the top and just kind of give you a general sense of what's happening. Our neuron is set up so that we take in an observation, we're going to weight it by multiplying it by some real number and then add a bias variable. And then we're going to predict out a numerical value in this case. We're just taking the linear combination and passing it through. And this number that we pass out of our neuron can represent anything that we want to, so long as it is somehow related to the input. So the general goal as we move forward is that we have an input variable that's associated with some number, or maybe even some class. And we want to tweak the weight and bias so that this neuron outputs something that is representative of the label or the categorical label or the numerical label associated with this feature that we passed in. Okay, so going down, back to my data frame. All right, so we've loaded our data. Penguins is the penguins data set. We have categorical species, categorical island, and then for each entry, we have measurements of bill length, bill depth, flipper length, and body mass. I do see that we have missing values here in our data frame. So I'm going to go ahead and drop those missing values in place. So I'm modifying the data frame with the drop missing bang, or the exclamation mark function. So this will get rid of all the missing values. And we can do that in this case because there's only going to be a few missing values in our data, as you can see from my previous YouTube videos on this topic. Okay, so up here we have the original data frame that had missing values. We did drop missing, and now those missing values don't appear. So before trying to train our neuron, let's visualize the data. And we're going to do this using the plots.jl package, and my preferred theme is the dark theme. Press Shift Enter, run that. So the data that we're going to focus on in our penguins data set is going to be limited to the flipper length versus the body mass. This is somewhat arbitrary and in that we could look at flipper length versus bill depth, or bill length versus bill depth. But I found that when writing this notebook, that these two were the best to kind of look at for our task of training our neuron to learn something. So let's look at, on the x-axis, the flipper length. And on the y-axis, we'll have the body mass. So for each instance of our data, we're going to have a pair, flipper length, comma, body mass. And we're going to plot that using the plots.jl package. In particular, we're going to scatter. So in the x-axis, we have the flipper length, y-axis, the body mass. This is a typo. I probably should have fixed that, but I'll do it here in the code. So I'm going to say scatter. So my penguin's data frame, bang for every row, and then put in the flipper length underscore mm. That's the column name. So that gets me all my x values. Penguins, bang, body mass column. That. X label, because you always need to label your axes. Flipper length, Y. So pretty sure I need to put in my units here, so millimeters. Y label will be body mass, grams. Color, I'm going to pass it a row of colors. So I like magenta. I also like light sea green and salmon. My markers will be, let's see, what do I like here in my notes? I like my diamond marker, hexagon, and star 7. And I also need to group these so that the colors and markers match up. So I'm going to group them by the species. Group equals penguins every row and species column. Shift enter. Okay. The first time you run a function using plots.jl, it's going to take a little bit of time. So let's just wait on that. Hopefully it doesn't take too much time. All right, so we see that we have a nice plot here. And maybe I forgot a title. I like to put my titles in. So title equals my penguins data. Shift enter, run that, and then we see the title appears. So when observing this data, we see that there seems to be a linear relationship between the flipper length and the body mass. We see that more or less for each of the 3 species, the flipper length body mass plots kind of form a line. And it's our hope to train our simple neuron friend to take in as input the flipper length and predict out a reasonable choice or guess for the body mass. So we're going to input flipper length and have our neuron predict out the body mass. If we go back up to our diagram here, the flipper length is going to come into our neuron. It's going to be multiplied by some weight. We're going to add a bias, pass that into our linear activation function, which basically just returns w times x plus b. And we're going to hope that our prediction is close to what the body mass should be. So flipper length comes in, and we want our neuron to say the relatively correct body mass. Okay, so going back down to my plot, Now, because we're going to be plotting this over and over again, what I'm going to do next is I'm going to write a function called custom plot to like be of use to us when we plot this data. So we can just call this function over and over again instead of having to type out this long sequence of things here. So for the sake of time, I'm just going to copy and paste this. I'm going to copy that, paste, and then now I'll describe to you what's going on. So the function is called custom plot. This is going to be a data frame object, which I call data. Actually, this is wrong. I'm going to have to do this from scratch. I will definitely keep some of this here for a moment. So, okay, I don't need this. All I need is my data frame, my column 1 name, my column 2 name. So these are like my features. So the input of this function has a data frame, X, Y. I'm going to pass it a neuron. And then I'm going to throw in a weight and bias. So, okay. What do I want to do? I want to say that when I pass in my node, I'm going to change the weight to be this weight that I put in, the bias to be this bias that I pass in. And I'm going to say capital X is equal to data, every row, my X entries. Little y is going to be data, every row, X2, so it's like my Y entries. The X min and X max will be the limits on when I plot the function with a figure, what my lowest X value will be and what my highest max value will be. The -10 and +50 are for visual purposes, which you'll see. And I want to scatter X, which is here, my Y, which is here. So this is feature 1, feature 2. Give them the labels X1 and X2. And then set my X limits to be there. Alpha here is a transparency argument for how transparent the scatter points will be. I'm going to group by the species in the data that I pass in, give these markers, give this color. I'm going to then plot X. So recall X is my X1, so like the X-axis features. And then I'm going to have my node predict what values should come out of those X entries. So imagine that these are all the flipper length values, and my node is just passing those flipper length values into its activation function. So on the y-axis for this plot, you're going to see a line representing how it interprets those input features. I'm going to give it a label neuron prediction and then color it yellow. So if I didn't do anything wrong, I think this will work. Okay. So I already have a node 2. But what I can do instead of making a new one is I can reset the weight to be random again. And I can reset my bias to be random again. And then I can custom plot this information. So custom plot, pass it in my data frame, which is called penguins. I already have the information here. So for the X, I have flipper length. For my body mass, for my Y, I have body mass. So again, up here, flipper length, body mass. And then next, I need to pass it my node, weight, and bias. Okay, so node 2. my weight, I'm just going to throw in node 2.w. And then for my bias, node 2.b. Press Shift Enter. Hopefully that runs. Oh no. Looks like something's going on with my access limits. Let me just go ahead and get rid of that. And then I see a plot. Okay. I'm not sure what happened here. X min, X max. But for the sake of time, I'm going to ignore that for now. So we see here that we have our data plotted, and in this yellow line are the predictions made by our neuron. So for example, I don't know how low that is, but like if I pass in 180 to my node 2 dot backslash p, pass in 180, shift enter, 130. So the value here is like 130. If I pass in 210, the value on this line here is like 151. And you can see our neuron is doing horrible at predicting the body mass. We're getting all these inputs. Our predictions should be over here near the data, right? So what we can do is that we can experiment with the weight and bias using Pluto.jl's HTML or bind functionality. Now, earlier, at the very start of the Pluto notebook, very top up here, let me get there, I imported Pluto UI. So because I imported Pluto UI, I can come down here and make interactive cells, okay? So the cells that I'm going to make are going to change the neuron, the node 2 weight, or not node 2 weight. The cells I'm going to make are going to change values of weights to pass in here and pass in here. And what that's going to do when we pass those in is it's going to change the node weight and the node bias. And I think the best way is just to show you. So I'm going to use the @bind macro, and I'm going to assign this to the variable w. Put in a slider. The minimum value of the slider will be -500. I'm going to have increments of 0.05, and then the maximum value would be 500. And then I'm going to give the keyword argument show value be true. And then in a similar fashion, I'm going to do that for b, the variable b. I'm going to run these cells now. Okay. And now over here in my custom plot, instead of doing node 2 weight, I'm going to just pass in w. That will update the node weight, the neuron weight. Pass in b. Okay. So by the reactivity and interactivity of Pluto, the plot changed because now the weight is -500, which is like the slope of our prediction line. And then the bias is -4000, so we're way down here on the axis. But we can change these. It looks like I need a positive slope, so let me like kind of change this a little bit, and you see the up. That's much closer. And I see that there is a positive linear relation here. So maybe I should raise my intercept or my bias some more. Kind of tweaking that over. Yep. Maybe increase my slope up. Too high. Maybe if I shrink down my bias a little bit. Maybe too high of a slope. Okay. So if our neuron has weight 35.7 and bias or intercept -31, so 3,000, -3,187.5, we see now that we more or less predict the values of body mass with input flipper length. So for example, here, flipper length of 190, let's pass that into our node's activation function, their prediction. 3,595. 3,595 is right here. And we see that that's in between all of the true body mass values for this flipper length. So what we've done is manually trained our neuron to make more or less okay predictions. That's kind of cool. So we've taught our friend, but how would our simple friend, our simple neuron, learn to do this on its own? Well, that's the realm of machine learning. So rather than manually tweak the weight and bias variables, we next program a machine to automatically learn these optimal values of weight and bias. This concept is known as machine learning. And the algorithm that we will use to automatically find the W and B is the gradient descent algorithm. But before we do that, we need to talk a little bit about scaling. So notice up here at the plots, the flipper length in millimeters is in the hundreds, whereas the body mass is in the thousands. This is going to really affect most machine learning algorithms. In particular, many machine learning algorithms, so in many machine learning algorithms, to bring all features in the same standing, we need to do scaling so that one significant number or feature values don't impact the model just because of their magnitude. Feature scaling in machine learning is one of the most crucial steps during the pre-processing of data before creating a machine learning model is made. Scaling can make a huge difference between a weak machine learning model and a better one. And one of the most common techniques of feature scaling is normalization. Normalization is used when we want to bound our values between two numbers, typically between 0 and 1. And because our flipper length and body mass data are positive values, we can achieve this normalization by simply dividing each feature vector, or each data point in the feature vector, by the maximum value of its respective value class. So for our flipper length, we could just divide by the maximum flipper length out of all of our observations, and we can assign that to X. This will be our capital X. This will be our input to our neuron. For the body mass, we just divide by the maximum body mass, and we assign this to the variable Y. So X will be our input and Y will be our output. So because I'm in a Pluto notebook, I need to create a block of code to do this. So begin. X is equal to penguins dot flipper length mm. So that's my flipper length column divided by maximum of penguins dot flipper length, like that. And then for Y, just to save time, I'm just going to go ahead and copy this code here. Same concept. And then end out that code block, shift enter. And now I have scaled let's see what my error here is. Okay, so let's look at oh, there's missing values. That was my problem. I must have not, oh, up here, I didn't do the exclamation mark. That's a big problem. The exclamation mark, the bang, is going to get rid of all of those missing values. And I didn't do that earlier. So now, coming back here, this should work. Because now there's no missing values and the maximum function works. If there's missing values, maximum will not work. Okay, so earlier we manually adjusted the weight and bias of our neuron by how well the output of our neuron predicted the body mass of our penguin data. Okay, so again, the better line that we made was better means, sorry, jumbling my words. The line that we fit is better because it's closer to all the data. And that's what we did manually. So, where am I? If our data is labeled this way, if we have M entries of data, so we have flipper length body mass for each of our penguins that are in a data set, we can measure how well our neuron is predicting by computing what's called the mean squared error cost function. This cost function is a function of our weight and bias for the neuron. And what is it? It's the sum. There is a typo that I just have to fix here. Fix that, okay. The mean squared error sums the differences between our output and the true value. Recall that yi is the true value of body mass, and yi hat is the predicted body mass given our current neuron's weight and bias. So this is like the distance between these two values. We want our prediction to be close to here. We square it to make it a positive value, which is like a distances have to be positive. So this is somehow like a measure of distance. We're summing over every possible data point we have. So how close are we to this y? How close are we to this y for each x that we pass into our neuron? And then we divide by m to compute the mean of the squared errors. And the 2 there is for convenience when we take the derivative later on. So here, oh, I guess I already wrote the code out. We have the cost function. So in this function, we pass in our x, our y, and then our neuron. First, we compute the length because we want to divide by m. So we do 1 over 2 times m times the sum of our prediction. Again, neuron prediction is y hat minus the true label, all squared, for each x label in zip of xy. So zip xy are just simply the pairs of x label. Okay, run that cell. So as before, we will next write a custom function to plot our data. And this time we're going to have our regression line as before, but we're also going to plot the cost incurred by our neuron's weight and bias. Okay, so here we pass in our data frame, x, y, our label for the x-axis, label for the y-axis columns, our neuron, our weight, our bias, and then legend equals true to by default add a legend. But sometimes we won't want to see a legend, and you'll see why in a moment. All right, so just for the sake of time, I'm going to copy this huge function here. Paste it. So this is custom plot scaled 1, so it's different from our other one. Pass in data frame, features, labels, column for features, column for labels, our neuron, weight, bias, and then a keyword argument legend to be true. Notice the keyword comes after the semicolon. That's when you start defining your keywords. So when we create this function, we pass W and B. That changes our node weight, our node bias. We compute the cost function, which we defined here. We set our x min, x max. Hopefully I don't get the same error as before. Scatter, feature, and then label values, those 2 numerical values. set our labels, xlim, transparency, group, marker, color, and then plot our nodes predictions for this choice of W and B. And then finally, we plot legends. So if we want the legend to be true, at the very end, this will show the legend. If we set that to be false, then the legend won't appear. So earlier, we changed our nodes weight and bias when we did this. So let's go ahead and reset our node weight and bias. So begin a code block, again, because we're in Pluto. Like that. So I'm resetting everything. Oh, not node, node 2. What am I doing? Again, node 2 is the one that can change. All right, so let's go ahead and custom plot 1. That's the function to name that. So I need to put node 2 here, node 2 here, node 2 here. Oh, I never ran my custom plot 1 cell. All right, so with the random weight and bias that we have, this is our prediction. It's not bad, but it's definitely not good. I don't like that my cost function is 0 right here. Did I define my cost function? So let me just test it real fast. So that's my cost. So I guess when it's rounding, it's getting like a, so maybe if I get rid of this round business here. So there's my true cost. Okay. So let's see if we can find a better line, or our node can learn on its own to find a better line. And the way that we're going to do this is with gradient descent. So I see that my battery is getting really low. I'm going to pause the recording and let my computer charge and be right back. Well, it looks like my computer died and had to wait a moment to restart it. But let's get started where we left off. So the algorithm that we're going to use to train our neuron is called gradient descent. And the way that this algorithm works is by heading in the opposite direction of the slope of the derivative. So there's tons of resources online for you to see this, and I don't really want to describe gradient descent in detail in this video. So in the description below, I'll provide one of my old lectures on the topic, as well as a few other places to learn more about gradient descent. But the idea here is that we want to minimize our cost function, right? We want to minimize the cost that we incur for a given weight and bias. We want to optimize our W and B so that this thing here returns the smallest possible value on our data set, right? For each I 1 to M, if we have M data points. So one way that we can do this is with what's called stochastic gradient descent. If we have M data points, instead of computing the gradient and going in the opposite direction of the gradient for each of the points, we can focus in on one point at a time, right? So for each, I should probably change this here. For each I up to M, we pass the X value into our neuron. It outputs this value in our cost function, right? So for each I, we have a value. We compute the derivative of the cost approximation function with respect to W, and we do that the same with respect to B. And we update our W and B accordingly. This should be a B right here. Now, each time we do this, so we pass through all of the data points M, this will be called an epoch. And we repeat this a number of times, always updating our weights and biases. So if we look at our cost approximation function, again, this is on one data point, not the full set of data. We see that the y hat is really a function of W and B. So if we take the derivative of this function with respect to W and use the chain rule, we get this value. So the coefficient of W here is X, so there'll be an X multiplying this difference on the outside. For the bias, there is no coefficient, so there'll be a 1 multiplying this difference on the outside. In Julia, this is really easy to implement. So we're going to write a function called stochastic gradient descent, bang, so that we pass in a neuron, and then we're going to update our neuron's weight and biases. So function, stochastic gradient descent, pass in our features, our labels, our neuron, our alpha, which is called our learning rate. I might have glossed over that earlier. So the alpha here is simply a scaling to say how far downhill do we really want to walk away from where we are currently. So this step length or learning rate will determine how quickly we change our weights and biases. It's scaling them. We don't want this to be too big. We don't want it to be too high. We want it to be just right. And the best way to do that is through experimenting. Next up, we're going to set a default parameter here, our epoch number, to be 10. So we'll run through our data set 10 times. All right, so for underscore in 1 to epochs, and then for X comma Y, in, so maybe instead of Y, I should use maybe label. For X comma label in zip X comma Y, so capital X versus little x there, I'm going to say neuron W minus equals, so I'm updating it, alpha, press tab, times neuron dot my activation function P, pass in my little x, minus label instead of y. I don't like using y over again like that, times x, and then neuron dot b minus equals alpha times our difference, so neuron activation, so p, pass in x, minus our label, which is the y value. No coefficient now because our bias doesn't have a coefficient. In that out, in that out, in that out. Okay, so let's now reset our node's weights to be random again. Our node weight to be random, and our bias as well. And let's train these to minimize our cost function. All right, so let's look at our custom plot here. So that's what our predictions are currently. So let's call our stochastic gradient descent function a few times and see what happens. So I'm going to write a code block here. So begin. Let's say plots is equal to an empty array. So I'm going to put plots in this to look at later. So for I equals 1 to maybe 100, I want to do stochastic gradient descent. and then bang. And then what are my arguments here? I pass in x, y, I'll just copy this. That x, y, my neuron's variable name is node 2. Alpha, I can just say is 0.001 as a guess. And let's do one epoch. So we're going through the data set one full time when we call this function, updating my node 2 weight and bias. And then if I is in 25, 50, or 75, I want to make a plot. P is equal to this custom plot thing with legend equals false. So that's just, I want to save the 25th, 50th, and 75th after gradient descent. And then end out my for loop, end out my code block. And then I also want to have an initial plot. So, oh, I never put my plot in my plots array. Push, bang, plots, I'm going to put in P. And then the same thing here. P is equal to this custom plot right there. Push into my plots array, P. So this is before we've done gradient descent. And then on the 25th time, 50th time, 75th time. Did I not define my function? Oh, I bet you I just spelled it wrong. Oh, I didn't put a bang. Bang. There it goes. So then there that goes. So I just ran this code block. Okay, so next up, I'm going to use the @layout macro to look at these 4 plots. So 2 on top of 2. And then I'm going to say plot L1. Oh, no. Plots 1. Oh, I wanted this to be true. I want the legend on the first one to be true. And then all the other ones to be false. And you'll see why in a moment. Plots 2. Plots 3. Plots 4. And then width layout equals to L. Oh, I can't do, what am I doing? I am in Pluto. I can only do 1 line of code at a time. In fact, I just should do this in a code block. There. So maybe it didn't learn very well. Maybe so I change my learning rate. Let's do like 100 epochs. Oh, we can see now that the line is starting to match up more. And it might have converged. So if we're looking at this is the last line here. I wonder what happens if let's start this over again because I'm going to reset my weights. And then, oh, this is still running here. Well, in any case, you can see that this line is much further away than these lines are here. And that was achieved by just running this stochastic gradient descent algorithm and optimizing the weight and bias of our neuron. So currently, our neuron is really predicting rather well, right? For this size flipper length, we're outputting this size body mass. And if we wanted this to train, oh, finally my cells are in, it's even closer. And we can translate this back to the original data by just taking the values and multiplying them by what we scaled them by earlier for the normalization. So we started up here, and then through gradient descent, we came down here. So the moral of the story, I suppose, is that a artificial neuron is nothing more than a function that we can manually tweak to get predictions that look like we want them to, or that we can optimize using an algorithm such as stochastic gradient descent to predict out a value. In this video, we did numerical predictions, but we could have also done classification predictions. And in the following 2 lessons on artificial neurons, I'm going to talk about classification. In particular, I'm going to talk about the perceptron algorithm and the logistic regression algorithm. And then finally, I'm going to talk about deep neural networks, all programmed from scratch so that you can program it from scratch on your own. If you like this video, please like and subscribe. Thank you for listening, and I'll see you next time.